everybody. So today we're going to be working on representations of functions as power series. Okay, so here the thing is, some functions can be represented as geometric power series. And our first example would be, let's say we have something like the sum from n equals 0 to infinity of x to the power of n. Let's write out what the terms are going to look like here. Right, so if we plug in n equals 0, we're going to get 1 plus x squared plus x cubed plus and so on, right? We just get higher and higher powers of x squared, x cubed, x to the fourth, and so on. And if we add them all up, we're going to eventually get, well, notice, sorry, what I meant to say is, here, notice what you're doing to get to each next term is you're multiplying by x to get to the next term. So we know that this is a geometric series since there's that common ratio between the terms, right? So each time you multiply by x, that means r is going to be equal to x, and the number that you start at, a, is going to be 1. So we can write it as a over 1 minus r, which in this case would be 1 over 1 minus x. So it turns out this function can actually be written as this power series. So that's kind of the basis for everything that we're doing today. And I'll say here, for this section, everything is built off of this one equation. So this is the most important equation to remember for this section, right? It's just that if you have this sum, it's the same thing as 1 over 1 minus x, and we're going to use that. So the reason why this is so important is, say here, by plugging in things other than x to this function right here, we can get power series representations of other functions. And that's the whole goal of this section. So let's start with example number 1. And it's going to say express 1 over 1 plus x squared as the sum of a power series. Okay. And the second thing it's going to ask us is to find the interval of convergence. Okay. So we need to figure out these two things. And the way we're going to figure it out is by relating this function to this function. And we see, what do we have to plug in for x here to get it to look like what we have there? Okay. So we'll say here, replacing each x in star, the equation that I wrote earlier, with negative x squared, then let's see what we get. If we replace this x with a negative x squared, then that's exactly how we get back to here, right? So that's why I chose negative x squared as the thing to substitute in there to get back to there. So as long as we replace all the x's here with minus x squared, then we're going to get what we're looking for. So what we say here is 1 over 1 plus x squared equals 1 over 1 minus negative x squared. And that's what we're replacing everything with. So we can replace this with the sum from n equals 0 to infinity of, so now we replace this x with a negative x squared to the power of n, right? So that's how we can write it as a power series, just by using this equation up here. And now we can break this up into different parts and say that this is the sum from n equals 0 to infinity of minus 1 to the power of n times x to the power of 2n. Okay. And now we just write out, well, what does this look like? Well, if you plug in n equals 0 here, then you're going to get 1. And then if you plug in the next term, n equals 1, then you're going to get minus x squared. Next would be plus x to the 4th, then minus x to the 6th, plus x to the 8th, and so on. Right? So that's kind of the pattern you get, is you just add 2 to the exponent each time, and this part means that it's alternating. And now we just look for the common factor in between these two, and you see that every time between every two terms, they're going to be multiplied by negative x squared. So this is a geometric series with common ratio negative x squared, which is kind of what we saw here, right? Because that's what we had to plug in for r, right? Because we can write this as a over 1 minus r, so that's going to be our common factor. Okay, and now so we can say here that this is a geometric series with r equals negative x squared. So remember, it's convergent when the absolute value of r, which is the absolute value of negative x squared, is strictly less than 1. So we just got to find when that's the case, i.e. the absolute value of x is less than, so this is the same thing as saying the absolute value of x is less than 1, because the minus sign goes away with the absolute value, and if x squared is between 1 and negative 1, well, you just take the square root of everything, and well, x is also between negative 1 and 1. Okay, and so now what we can say is we can just turn this into an interval. So we can say, so the interval of convergence is the interval from negative 1 to 1. Right, and you might be confused here because remember earlier what we were doing was we also had to test the endpoints. We had to be very careful to do that. But that was when we were using the ratio test. That's when you have to test the endpoints. Here we're just using the fact that this is a geometric series. You don't have to test the endpoints there because if L, this was L, or sorry, not L, L was the ratio test. If the absolute value of R, that's what I meant to say. If the absolute value of R is equal to 1, then the common ratio is 1, so you just keep adding something to itself. And if you do that infinitely many times for something that's not 0, then you're going to get infinity, so it's going to diverge. So using the geometric series test, this is always going to converge exactly when the absolute value of r is less than 1. Now, our second example here, number 2, is going to say find a power series representation of 1 over x plus 2. Okay, so with this type of problem, let's just rewrite what we have. So we've got 1 over x plus 2. And let's see how we can rewrite that. Well, notice here, in this formula, we've got a 1 here, but now we have a 2 there. So I want to change that 2 into a 1. So the way I'm going to do that is rewrite this as 1 over 2 times 1 plus x over 2. Okay, so I'm going to go ahead and do that step, because now this allows us to take out this factor of 1/2. So if we do that, we're going to have 1/2 times 1 over 1 minus negative x over 2. Okay, and now we can see, we can do what we did in example 1 to rewrite this thing. Okay, so that's our next goal. So we can rewrite this as 1/2 times the sum from n equals 0 to infinity, where we replace, here this was x to the n, we replace that x with this thing here. So we're going to have negative x over 2 to the power of n. And now we can just rewrite this. So this is 1/2 times sum from n equals 0 to infinity of, now we can rewrite this as negative 1 to the power of n times x to the power of n over 2 to the power of n. Okay. But 1/2 times 2 to the n, you can rewrite as 2 to the n plus 1. So we can rewrite this as n, sum from n equals 0 to infinity of negative 1 to the n times x to the n over 2 to the n plus 1. And now, if we wanted to write out the series, we can do that. So if we did that, we wrote out the series, we're going to have, so if you plug in n equals 0, you're going to get 1/2. If you plug in n equals 1 minus x over 4, and then plus x squared over 8 if you plug in n equals 2, and then minus x cubed over 16, and so on. So this is enough for us to try to establish a pattern. Here, we're multiplying by negative x over 2. Again, we're multiplying by negative x over 2. Again, we're multiplying by the same thing, negative x over 2. So that's going to be our common ratio, is negative x over 2. So let's flip to a different page here. So we saw that was our common ratio. So we can say that our series converges when the absolute value of x over 2, which was our common ratio, sorry, negative x over 2, is less than 1. Right, so we just got to figure out when this is true. So we take the absolute value, we're going to have that negative 1 is less than x over 2 is less than 1, right, because that's what the absolute value means. And then we just multiply everything by 2. Negative 2 is less than x is less than 2. So now we can see that our radius is going to be, well, here our interval of convergence is going to be from negative 2 to 2. And here our radius, which is 1/2 of the length of the interval, would be 2. So our radius is also going to be equal to 2. And again, I'll say here that we don't need to test the endpoints because this is a geometric series. We're not using the ratio test. Okay. Now, let's talk about differentiation and integration of power series. Okay. So for this topic, we're going to need a theorem. This is actually the only theorem in the section. And it's going to say if the power series so let's write it as the sum of Cn, our constant term, times x minus a to the power of n has a radius of convergence r, which is greater than 0, then the function f defined by f of x equals the sum from n equals 0 to infinity of Cn times x minus a to the power of n is differentiable on the interval from a minus r to a plus r. And so the first thing is going to be that f prime of x is going to be equal to sum from n equals 1 to infinity of n times Cn times x minus a to the power of n minus 1. And part 2 is going to say that the integral of f of x dx equals c plus the sum from n equals 0 to infinity of Cn times x minus a to the power of n plus 1 over n plus 1. Okay, right. So let's unpack exactly what this theorem is saying. We're saying, say we start with some function that's going to be differentiable on this interval. Then what we can say is that we can take the derivative of this function. So f of x is equal to this. And what it's saying is the derivative of the left side, which is f prime of x, is going to be equal to, on the right side, the sum of the derivatives of the right side. Right? So it's just, we're taking the derivative of each term. And the way you do that is you take out the n, which is what we did here, and then you reduce the exponent to n minus 1. Right? So that's how we take the derivative of each term. That's just what we normally do to take the derivative of something like this. All this theorem is saying is you have to be a little bit careful when you have these infinite sums, but this theorem is saying if you satisfy the hypotheses, then to take the derivative of this function, you just have to, to take the derivative of the power series, which is the hard thing to figure out, you just have to take the derivative of whatever function is equal to. And the same thing for the integral, you just take the integral of each term, which is what this is. Okay. So I'll say here the radius of convergence in 1 and 2 is going to be r, which is what it says there. And also, the intuition check we can check here is that the derivative or integral of a power series should just be the derivative or integral of each term, which is what we wrote down. Okay. So let's write down our next example. Example number 3. So, example number 3 says express 1 over 1 minus x to the power of 2 as a power series by differentiating equation star and what is the radius of convergence? Okay. So I'll say here, remember that equation star was the equation that said if we have 1 over 1 minus x, that's going to be equal to the sum from n equals 0 to infinity of x to the power of n. Right, so that's the thing that we're going to keep using in this section. And what the theorem says is that the derivative of the left side is equal to the derivative of the right side. So if we have, let me use a different color here. So if we have the derivative of 1 over 1 minus x, that's the same thing as the derivative of 1 minus x to the negative 1. Right? Oh, sorry. It's just going to be a derivative. Right, so we're taking the derivative of 1 minus x to the negative 1. And if we do that, we need to use the chain rule. So we take out the exponent, the minus sign. We take the inside function to the power of this number minus 1. So it'd be negative 2. And then we have to multiply by the derivative of the inside function. And that would be negative 1. So the minus signs cancel out. And we're going to get 1 over 1 minus x squared. Right, so this minus sign was coming from taking out the power, but then this minus sign was coming from taking the derivative of the inside function. Okay, so that's what we get using the chain rule, and what the theorem is saying is that the derivative of this is equal to here where we take the derivative of each term. Right, so this function, which was what we were interested in, is going to be equal to the sum from n equals 0 to infinity. So we said this derivative was the same thing as 1 over 1 minus x to the power of 2. And then this derivative is n times x to the n minus 1. Right, that's using the power rule. Okay. And so all this is saying is the derivative of the left side, which is this, is going to be the same as this. So we actually already found that. So we found our answer. We tried to find the power series. That's our answer, but just let's write out the terms of this power series. We write out the terms starting at n equals 0. We've got 1 plus 2x plus 3x squared plus 4x cubed and so on. Those are going to be the terms. And we can say here that the radius of convergence right, so here we look at what we're multiplying by. We're multiplying by 2x. Oh, sorry, that's not what I meant to say. What I meant to say is here, whenever we look at the theorem, the radius of convergence is this, and what I meant to write down here was that the radius so I just said this in words earlier, but actually it's probably important to write down of the series in 1 and 2 is R. Right, so I should have written this down earlier. I said it in words, but I should have written it down, because the way we find the radius of convergence of this derivative is we say, well, it's actually the same thing as the radius of convergence of the original function. So here the radius of the convergence of the original function we said was 1. That's what we figured out, I think in example 1. And this is going to have the same radius of convergence. So the radius of convergence in this example is the same as the original function, so is r equal to 1, right? So that's how we find the radius of convergence. Okay. Now, we've just got one more example to go through. Okay, example number 4 is going to say find a power series representation for the natural log of 1 plus x. Okay, so let's try to think about, well, we can try to use this theorem. It's not going to be taking the integral of this thing might not be all that helpful, but we do actually know how to take the derivative of this thing. So note that the derivative of the natural log of 1 plus x is going to be equal to, so if we take our derivative, again we have to use chain rule, it's 1 over the inside function times the derivative of the inside function, but the derivative of 1 plus x is just 1. So the derivative of this function is 1 plus x, which we can say now means that the derivative, so the integral of 1 over 1 plus x dx. So if we take the integral of both sides, then we're going to get that the integral of this is equal to the natural log of 1 plus x. Okay, and now let's use a fact. Right, so we want to find a power series for this inside part here, the integrand. We want to find a power series for this part, and then take the integral using this theorem, and that's going to tell us how we can represent our original function as a power series. So we've got to first worry about this inside part. So 1 over 1 plus x, we can rewrite as 1 over 1 minus negative x. And now we use that equation that we wrote down in the beginning, and we just substitute in negative x into that equation. So if we substitute in negative x into the equation I wrote in orange, we can now say that this is the sum from n equals 0 to infinity of negative x to the power of n. And we can, of course, rewrite that as sum from n equals 0 to infinity of negative 1 to the power of n times x to the power of n. Okay, so we figured out how to rewrite the inside part here. And now we've got to take the integral of this power series, but we said we can just use this theorem to take the integral of each term of the power series. Okay, so we know that the natural log of 1 plus x was going to be equal to the integral of 1 over 1 plus x dx. And we already have a representation for this part on the inside, so we can rewrite this as the integral of the sum from n equals 0 to infinity of 1 over 1 plus x, or, oh, sorry, that's not right, of negative 1 to the n, x to the n. So the integral of this thing with respect to x. And now we said with the theorem we can pull the integral symbol into the inside. So the theorem says we can rewrite this as the sum from n equals 0 to infinity of the integral of -1 to the n, x to the n, dx. So now the integral part is actually on the inside. And now we can take that integral, saying that the integral of x to the n is x to the n plus 1 over n plus 1. So now this is going to be, remember we always have to add our constant c to these problems, plus the sum from n equals 0 to infinity of, now this would be -1 to the n, x to the n plus 1 over, oh sorry, this is a bit sloppy, x to the n plus 1 over n plus 1. And now the last part of the problem is we need to figure out what c is equal to. So if we're able to, we always want to figure out what this constant is equal to. So let's just consider, note, if x equals 0, then what happens if we plug in x equals 0 into this? So we're going to plug in x equals 0 here, and we're going to plug in x equals 0 here. So if we plug in x equals 0 here, then we're going to get the natural log of 1. And now if we plug x equals 0 into this function, all of this stuff goes away, so we're just going to get c. Right, so natural log of 1 is equal to c. And now we can solve what the natural log of 1 is, because it's saying e to what power gives me 1, and the power has to be 0. So anything to the power of 0 other than 0 gives you 1. So c is equal to 0. So now I actually can say that this part goes away because that number is 0.